Ancient civilizations developed numbers to measure tracts of land, track the paths of planets, and balance ledgers in commerce. If you couldn't see it or touch it, it didn't belong in the math. This animated diagram shows how ancient mathematicians approached algebra. Take the equation x squared plus 26x equals 27. To them, x squared is a literal physical square. 26x is a rectangle. To solve for x, you can cut that rectangle in half and arrange the two pieces around the square. You're left with an almost complete larger square, missing only a small section in the corner. By adding a 13 by 13 piece to both sides of the equation, you literally complete the square and reveal the positive mathematical solution. But if you run the raw numbers, negative 27 is also a correct answer. Ancient mathematicians completely ignored this. A shape with sides of length negative 27 makes absolutely no physical sense, so negative numbers were considered impossible. Then mathematicians hit a wall with the cubic equation. For 4,000 years, every civilization tried to find a general solution for an x-cubed term. In the 1500s, holding a job as a math professor in Italy was highly precarious. Your position at a university was never secure. It was constantly threatened by rival scholars. These disputes were settled through public math duels. Challengers would trade lists of complex problems. Whoever solved the most won the position, while the loser faced public humiliation and unemployment. This vicious environment meant mathematicians did not publish their discoveries. They hoarded their formulas, treating mathematical proofs as secret weapons to secure their livelihoods. Sometime around 1510, a professor named Scipione del Ferro figured out how to reliably solve a specific type of cubic equation. He kept it entirely to himself for nearly 20 years, only whispering the secret to his ambitious student, Antonio Fiore, on his deathbed. Decades of hiding answers from the public had built up an academic pressure cooker of jealousy and ambition, and Fiore was eager to exploit his newly inherited weapon. Fiore issued a challenge to Niccolò Tartaglia, a battle-scarred, self-taught mathematician. His entire career on the line, Tartaglia locked himself away. Recognizing that a solution must exist, he managed to derive the secret rule himself, solving all 30 of Fiore's problems in a matter of hours. Tartaglia pushed the idea of completing a square into 3 dimensions, solving for physical volume. Padding out the original cube breaks the volume into 7 shapes. Rearranging 6 prisms into a single block effectively reduced the impossible cubic down to a solvable quadratic equation. Tartaglia had weaponized the physical geometry of the ancient world, pushing 3D spatial reasoning to its absolute limit to solve abstract algebra. A wealthy polymath named Girolamo Cardano noticed Tartaglia's sudden rise. Through aggressive flattery, Cardano lured Tartaglia to Milan and extracted the secret algorithm under a solemn oath of silence. Cardano was forced to expand a square with an area of 25 to an area of 30, while strictly keeping the side lengths at 5. This required adding an impossible physical space, a negative area. The formula outputs the square root of a negative number. 10 years later, an engineer named Raphael Bombelli decided to push straight through the paradox. He treated the square root of a negative as a temporary phantom number. He assumed if he kept calculating, these bizarre negative roots would eventually cancel each other out, leaving behind a perfectly normal, real answer. To find the correct answer, mathematicians had to detach calculations from physical reality. Geometry was no longer the ultimate truth. This detachment liberated modern algebra. Decades later, René Descartes heavily utilized these phantom figures, coining the mocking term imaginary numbers, and Leonhard Euler eventually assigned them the letter I. Fast forward to 1925. Physicist Erwin Schrödinger is desperately trying to build a wave equation that accurately governs the behavior of subatomic quantum particles. He discovered that he was entirely unable to model the physical universe without writing I, the imaginary number, directly into his fundamental equation. This graph shows how imaginary numbers actually function. They exist on an axis entirely perpendicular to the regular number line, creating the complex plane. Multiplying a value by I doesn't just scale it, it rotates the point exactly 90 degrees around the origin. By stretching those rotations along the x-axis using an exponential function, you get a continuous 3D spiral. If you look at the shadows this spiral casts on the walls of the graph, it projects a perfect cosine wave on one side and a sine wave on the other. This complex wave math perfectly dictates the quantized orbits of atoms. It forms the strict mathematical basis for all of chemistry and most of modern physics. Nature literally operates using complex numbers. We only understand the invisible quantum mechanics of our universe today because a few ambitious men in Renaissance Italy were forced to invent